Hello fans, still here in Kungsparken in Malmö. I want to talk a little bit about how do we know what elements make up the sun? What elements make up other plasmas in space? We cannot go there, take a bit of the sun and bring it back in a box and measure it. We cannot do that. We have to understand the makeup of the sun from information it is sending us. And we have a small instrument here which is slightly better than my simple DVD here. It is called a spectrometer, an optical spectrometer, and it has inside four components. One actually is a piece of DVD like this, or what we call a diffraction grating. When I use the DVD disc like this, I'm using it as a diffraction grating. And actually this one is better than the one used by Anders Ångström in Uppsala. The important thing about a diffraction grating is the distance between the grooves on the surface of the DVD, for example here, or on a diffraction grating. The distance between the grooves related to the wavelength of the electromagnetic spectrum you're trying to resolve. And I'm looking at visible light because that's all my eyes can see, obviously. And from the work of Ångström in 1864, we know wavelengths of light is around 500 nanometers, or 0.5 times 10 to the minus 6 of a meter, or 0.5 thousandths of a millimeter. If you imagine 1 millimeter, and you can then divide that more than 1,000 times, that is the separation of the grooves on this DVD here. The separation here is 0.75 thousandths of a millimeter. We can do better than that with machines we have now for ruling such diffraction grating. But this one is fine, because the wavelength of light is around the same. Red light has a wavelength of about 0.75 times 10 to the minus 3 of a millimeter. Therefore, this behaves perfectly as a diffraction grating for visible light. There is such a thing inside here, smaller obviously. There is a concave mirror for collecting light. I don't need that when I'm using the sun, but you could use this for other light sources. There is a convex mirror, which will then give a parallel beam of light onto the grating. This is important, and we can, in a future video, actually go through exactly what you need to make a spectrometer. You can do it at home. You can make spectrometers on your home. They're not difficult. Components, a DVD, a few concave lenses or mirrors, and finally, some way for detecting the light. How to capture what we call the spectrum, the breakdown of colours as a function of intensity. How to capture that. When we use a DVD, I'm using my eyes as the final detector. Inside here, we're using what we call a CCD, a charge coupled device. Those are the same kind of light detectors you have in your mobile phone. The one that is filming me at the moment is a CCD detector. That is what we have inside this little box here. We have concave mirror for collecting light. We have a DVD for diffracting the light and making this rainbow. We have a concave mirror focusing the light onto the detector, and we have a CCD. What I know and what I can tell you is the amount of light, the amount the light is spread out, which makes it more resolved. It depends on two things. One, the distance between the grooves on my diffraction grating or DVD, and the focal length of the concave mirror that focuses the light onto the CCD detector. So you can argue that the diffraction grating inside here has roughly the same distance between the grooves as my DVD disc. It doesn't need to have any difference because that's already roughly the same as the wavelength of red light, for example. The other thing that matters when you're talking about the amount that the spectrum is diverged is the focal length of the converging mirror, which here is about 5 centimeters. My eye, I've measured this, is about 2.5 centimeters. Therefore, this is about 2 times better than this at giving me a resolved spectrum. That, looking at sunlight, I just see, in this case, a series of colours, a rainbow. If I look in more detail, I can see dark bands in here. They are absorption lines of elements like sodium, hydrogen. By comparing the spectrum, detailed spectrum, of the sun collected by something like this, which then puts that spectrum onto my computer, with spectra of elements taken under control conditions in the laboratory. Ångström, Anders Ångström, worked on hydrogen. He recorded the spectrum of hydrogen. He then looked at the spectrum from the sun, and he saw the same features. And he said, there's hydrogen in the sun. That is the way we do it. Thank you.